Okay, so far we have seen the collision and collision resolution technique. We have already seen the chaining method and table doubling for the chaining, the load factor of the chaining method, and the complexity of table doubling. Okay, so these things we have already seen. That is a very good technique for collision removal. We have another one collision removal technique we call open addressing. Hmm. Open addressing, it is simple, but sometimes it's increase the complexity. So, but as a part of this syllabus, addressing, let me cover this open addressing. Let's say we have usual, we have elements K1, K2, Kn, n elements corresponding n key corresponding to n elements, and we have the hash table and we have hash function. Okay, this is our hash table. Let's say T. Okay, size of the hash table. Size of the hash table is M. So, what is our objective? Objective is to keep this n element. We have to insert n element, and we have the size of table. Okay, so our objective is to keep n equal to order of m. Okay, if we take very small size of table, then there will be lot of collision. Okay, there will be lot of collision, and we cannot afford all the element in this table. So m must be greater than n, but m should not be too large. Too large means wastage of memory. So now, if m is not too large, let's say m equal to 2n, okay, or 1.5 n. That is quite good, but there will be collision. Okay, because we have birthday paradox. Birthday paradox says there will be collision. There will be collision. Now, how to handle this collision? Open addressing method says when we have collision, we can shift to the other position nearby where there is no collision. Okay. For example, let's say K1 is inserted here uh, and K2 is inserted here and K7 is inserted here. Okay, in this way. Now we are inserting, let's say K11, and K11 is coming at this place. So open addressing says, so what we can do if there is a collision, then we can insert it in somewhere other location where the table is empty, because table size is already bigger than n. Not all the position slot can be open. So there must be some open position. So what we will do, we will insert the element. Let's say K11 can be inserted in the next location. Okay, if it is empty. If it is not empty, then we will go to next location. Okay, so that is called actually linear proving. Linear proving. What we do is we write x and hx equal to a function. Okay, whatever the function we have defined plus I into plus 1 into k. Okay, where this you can write directly k, where k equal to 1, 2, 3. Okay, in this way. So k is we will increase the k, and we can basically write this output in this way. So we can write the out of the index as hx k. That is the better representation. We can write the output of the index. So for example, let's say hx value is 7. Okay. So we will write 7 means first port. Okay, they will be 0 1. So 70 means first port, means its actual location. So if we are writing 71 means next location, 72 means next to next location. So in this way we can identify the index, but we have to maintain one more variable with this. That is one of the implementation. Or if we are not maintaining these things, we will blindly search next location until the element is found. Okay, if the element is not found, after scanning the whole table, we will say the element is missing. So for uh, absent of element, in the worst case, we may have to search the whole table. So that will cost us order of name is larger than n, so we can write order of n. Okay, because m may be 2m, so we can directly write order of n. So the probing method is good. We can occupy the empty slots and we can make a compact hash table and remove the collision, but it will increase our complexity. The main objective of the hashing to maintain a complexity of order of 1, that may become hard. There are other method of probing. Instead of uh, one, we can go for quadratic probing. Which allow us, instead of going to next location, we can go for 1, then 2, then 4, then 9 in this way. So this type of probing called quadratic probing, or linear probing, quadratic probing. We can probe with arbitrary function. That is also possible if you want to implement using any arbitrary function. That is also. So that's all of the probing technique. It is simple, but it uses some more complexity. Especially if the table size is very large, any whole table for every element is not the desirable. That is almost equal to the searching in the array. Okay. That's all in probing.